Hello friends, welcome to Coding Interviews channel. Hope you're doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created a bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, trees, queues, linked list, etc. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from the description section of this video. Let's jump into today's problem. Search insert position. Given sorted array and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order, right? So basically we were asked to see if you can find a target element in the particular given array. So, and we already given that information that the array is already sorted. So there are two conditions here, right? So one is when the target value is found, you are supposed to return the target, right? Target's index basically. But if it is not found, what we are supposed to return is if you were to insert this particular element into the array by preserving the sorted order, where that index would be, right? So that's the question asked. So there are two different conditions here, right? And you can assume that there are no duplicates in the array, right? So we can go ahead and simply look at like basic approach, and then we will try to evolve from that approach to the new one, right? So what we can do is we will look at every single element starting from the index 0 and see if it is less than or equal to target, right? So we go on search for this particular index, particular element, and if it is less than or equal to target. So we stop wherever we fail that condition. That means the target is found or the target's location could be at that particular index. But if the target is found, we just return that particular index. But if the target is not found, that means we have exited that particular loop, but the elements, the current element is greater than the target. That means we have to return the appropriate index. So it could be index +1 or the current index -1, whatever that is, right? So we will have to return accordingly, right? So just for that particular case, we are going through the entire array. What if the target is not present, right? What if the target is not present? The second case as described in the problem, right? So if the target is not present, you will have to go through all the given numbers and realize, oh, okay, I don't have that particular number. So for example, I have like an array for like 2000 different elements, and then the target given is, let's say, 7000, right? So in that particular case, you'll have to go through the entire array and realize, okay, all these elements are less than my target. So my target should occur at the end of the the particular array, right? So it's like you'll have to go through the all elements but realize the target is not present, right? But if the target was 0, let's say, right, if the target was 0, you don't have to go through the entire array, and you can realize, okay, first element itself is greater than the target. You'll say just, okay, return 0. That would be probably the best case. But the worst case, you'll have to go through all the elements in the array, right? So let's try to scrap that approach and go to the second approach. So in that first approach, what we are not using is the intelligence of the array is already sorted, right? So now let's use that property that the array is already sorted and try to employ a different technique, right? So when the array is sorted, there is a technique available in order to search for a given target, that is a binary search, right? So we will employ a binary search technique in order to solve this particular problem to find the insert position. So we can have like 4 different cases when we are trying to do the problem with the binary search, right? If the target is present, that will be a classic binary search problem. We will be able to return the index as soon as you find the target. But what if the target is not found, right? So if the target is not found, there are 3 different cases that are possible. The 3 different cases are: the target could be less than all the elements in the array, just like I had an example like this, right? Target is equal to 0 and you have all these elements, right? That is one thing. And the target could be greater than all the elements in the array, just like 3000, right? So the maximum element here is 2000 and that target is 3000, right? So that is the second case. The target is greater than the elements in the array, and the target could be somewhere between two elements in the array. Let's say the target could be 4 in this particular case, right? So 1, 3, 5 is there, but 4 is missing, right? So the target could be 4. That means it is somewhere between two elements in the array, right? See, these are the like 4 different cases for this particular problem, right? So the first case, the target is present, we can tackle through the classic binary search algorithm. But the other 3 cases, we will be extending the binary search logic to employ these three cases also, right? So now what we are going to do is we will go through the examples first to understand, and then go look at the code, right? So the example 1 case, right? So this is a classic binary search case where you have all the the target element is already present in the array, right? And example 2 case, that means the 2. So it should come between 1 and 3. So we have already seen in this case, right, the target is equal to 4, where it's supposed to be between 3 and 5. So example 3 and 4 are basically the things that we already looked at. The target is less than the element and target is greater than the elements, right? So let's go ahead and look at the code first, right? So we are not looking at the code for the approach 1, but I'm going to directly show you the approach 2 code, right? So let's go ahead and look at the code for that. So search insert. So in the binary search algorithm, right? So first we get the starting and end points, right? So for that we just get the length of the array first. But before proceeding, we check the length of the array. If it is equal to 0 and we are trying to find a target, that means length of the array 0 means you don't have any elements in the array, but you are trying to search for a target in the empty array. That means if you were to insert the target into the empty array, the index position would be obviously 0, right? So that's why you return 0, right? That's the first case. Basically this is the case that we did not even discuss, but this is the base case that we would say. That's why I'm tackling right now before entering into the classic binary search, right? So after that I have declared a start and end indices, where start is pointing to the 0 and end is pointing to the n-1, because the arrays in C# are 0 based. That's why I'm starting with 0 and ending at n-1, right? So next comes the classic binary search code. While start is less than end, we calculate the midpoint and see if the midpoint is equal to target. So that's the first case here, right? So in our analysis, this is the first case. The target is present. If the target is present, you are going to return that particular index straight away. There is no problem at all, right? So but if the target is not present, right? So that could be, the target could be, the midpoint is greater than the target. That means your search, right, the binary search should go on to the left side of the array, right? So that means we are capping our search with the endpoint as mid-1, right? So in binary search, what we are going to do is, at every comparison we are cutting the search space into half, right? So first we check whether it is equal to target. If it is not, we cut the search space into the left half or right half. So if the midpoint is already greater than the target, we are cutting the search space into the first half. So we are going to continue to search for the target in the left half of the array. But what if target midpoint is less than the target? That means you are continuing the search into the right half of the target. So that means you are reinitializing the start to the mid+1, right? So that's how we are able to split the search or cut the search space into half every comparison, right? So once we come out of this while loop, that means, what does it say? That means you are not able to find the target. That is, we are coming to the second case, right? If the target is found, we were returning the mid anyway, but now we are coming to the second case, right? Target is not present in the array. So what we are going to do, there are 3 different cases. So in these 3 different cases, we are again we will tackle these 2 cases first and then come to the first case, basically when the target is less than the elements in the array. So now going for the last two cases, right? So if the start is less than or equal to end, so basically if the start index is less than or equal to end, that's what we are checking here. If that condition is still holding, so previously we are only checking here in the while loop less than or equal to end, right? But here once it is out of the while loop, less than end, but here we are doing less than or equal to end. If that is the condition satisfied, right, and then we check if the end is still less than the target, that means target is more than the end element, right? In that particular case, what we are going to do is just return n plus 1. That's what it is, right? So whatever the elements are so far that you have been observing, the end is still less than the target. Obviously then the target element should come at the end plus 1 position, right? So that is what these three cases. Target is greater than the elements and target is somewhere in between two elements, these two cases. And the first case, the target is less than the elements. That means it should be the very start position, right? That's what we are returning. Otherwise, we just return the start position, right? So that's how we have extended the binary search algorithm to cater our need of search insert position, right? So it is tackling 4 different cases. The target is found, target is not found, and the target is greater than the elements, target is less than the elements, target is somewhere in between the two elements in the given array, right? So let's go ahead and look at the time and space complexity for this particular algorithm, right? So time complexity for this, right? We are going through the entire array here in the while loop, but at every comparison we are cutting the search space into half, right? So if your array is 10 elements, right? So at the first comparison you are cutting that into 5 and then 2 or 3 and then 1, right? Basically you are cutting down. So what does that say is the time complexity for that particular approach is order of log n. So that's what I have given here as the time complexity, right? And let's look at the space complexity. Are we using any space here? Yeah, we are using few variables here. N is a variable, start, end, and mid. So these are all few variables, right? 4 different variables that we are using. But if the length of the array is, let's say, 1,000,000 elements, still we are using only these 4 variables. That means we are using a constant amount of space for this particular algorithm. That's why I have given it as order of 1, which is a constant space. So binary search based algorithm is log of n time and order of 1 space. Okay. So just for the comparison, right? So we have already abandoned our first approach, but let's see how much time complexity and how much space complexity we were able to improve with the approach 2 over approach 1. So let's go back and look at the time complexity. The time complexity in here is, in the worst case, when the target was 3000 and only the 2000 elements are there, and the 2000 was the maximum element in here, right? In that particular case, we have been going through all the elements in the array, right? So what does that say? The time complexity for this particular algorithm will be order of n, and the space complexity is still constant. So we are not using any extra space except the comparison, probably the indices, right? So the space complexity will be still order of 1, that is a constant space, but time complexity is order of n. So if you compare the approach 1 and approach 2, right, space complexity, there is not big improvement because it's already a constant space and we preserved that constant space. But for the time, it was order of n with approach 1, but we were able to see multifold increments with the approach 2 for log n, right? So if you have any further questions, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted the code for this problem to the GitHub repository. You can find the link in the description section of this video. If you haven't subscribed to the channel yet, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe. Goodbye.